Electric force in 2 dimensions. So far, we've only looked at the force between charges on a straight line. If we have 3 or more charges that do not fall on a line, we must add the forces just like we added vectors that were at angles to one another. This was done in kinematics, dynamics, and momentum problems. We're now working in 2 dimensions. First, establish perpendicular axes that are symmetric to the problem. Here's the problem we're going to solve. Calculate the force on the charge at point C due to the charges at points A and B in this diagram. The charges at each point are equal to plus Q. So here we have the same charge on all three locations. We have a triangle with 3 equal sides. So therefore, what is the angle here? Well, 60 degrees, right? 60, 60, 60, add up to 180. Let's choose some axes for the problem to take advantage of the symmetry of the charges. A Cartesian coordinate system centered at point C will work well here. Draw the forces acting on the charge at point C due to the charges at A and B. Well, all 3 of these charges are positive, so the forces on C are going to be repulsive. So there will be a force this way due to charge A, and there's going to be a force this way due to charge B. And they will be equal in magnitude since these are equidistant, so they're both a distance r away from this charge, and both of these charges have the same magnitude. All right, so once again, since the charges at points A and B are equal, that will mean that the forces here are equal in length. The magnitude of those forces are the same, also because these distances here are the same. So now we're going to resolve the forces into components that lie on the x and y axes, observing that the angles made here are both 60 degrees. So this angle is going to be 60 degrees, and that angle is going to be 60 degrees. We now see that the x components of these forces are equal in magnitude. So this vector here is equal in magnitude to this vector here, but they're in opposite directions. So they're going to cancel out. This leaves the y components, which are equal in magnitude, and they're in the same direction. So we're going to add them together. Time for math. Let's focus on the y-axis first. So force AC, so that is this force here, is equal to force BC, and the magnitude of that force, we're just going to call it capital F. The magnitude is given by Coulomb's law. Now, since these charges are both positive Q, we have Q and Q instead of Q1, Q2. They're the same, so it becomes Q squared, and the distance between those charges is R. So that force, this force here, has a magnitude of K Q squared over R squared. This force here also has that same magnitude. Now let's focus on just the y components. So the net force in the y dimension is going to be this component plus that component. Now what are those components? Well, we know this is theta here, and it's opposite, so it's going to be related to sine. So our hypotenuse is F. So if we have F times sine theta, that will give us the length of this side of the right triangle. So here we have FAC here times sine theta. So this piece right here is going to be the length of this vector. We do the same thing for the other force. So FBC is the hypotenuse here times sine of this angle is going to give us FBCY right there. And these are both just F. We can eliminate these subscripts, and we see we have F sine theta plus F sine theta. That's just 2 F sine theta. Now we're going to plug in our numbers. So 2 times F, which we've already said is K Q squared over R squared, times sine 60 gives us this as our answer. In the x dimension, the forces cancel out. So it's not as interesting. Those just add up to 0. So therefore, the total force is going to look like this. It's going to be twice as long, right? So it's this vector plus this vector. So it'll go straight up, and it's going to have a magnitude of the square root of 3 k q squared over r squared.